Okie dokie, Chapter 2, Observing the Sky and the Birth of Astronomy. Okay, so chapter outline. The sky above, ancient astronomy, astrology and astronomy, and the birth of modern astronomy. So this is kind of taking us through sort of the early observations that led to what we consider the modern scientists. So we're talking about a member of the Flat Earth Society moving next door and trying to tell you that the Earth is flat, okay? And obviously Earth is not round and so on. Obviously a joke, maybe not obviously, because maybe it is a conspiracy and maybe you're not in the loop. Have you ever actually seen the edge of the Earth? Have you flown around the planet? Well, until you do, I guess you can never be sure. But we're going to talk about how you can test this, even yourself, even between a few cities close in Iowa. Okay, so the main thing from this chapter is to understand this idea that we call the celestial sphere, which is the system that astronomers use to describe the sky, this right ascension and declination, and the celestial sphere. And then talk about how the motions appear to us, the sun and the motion of the moon and the planets, and what a constellation is. So that's our goal for this chapter. So important word here is this idea of a geocentric world, and a geocentric world means Earth-centered, and this was the thought that the Earth was the center of the universe, and also the center of the solar system. So all the planets orbited the Earth, the sun orbited the Earth. Of course, you would assume that right away. Why wouldn't you? You're a human with a massive ego. You may as well go all out, right? The geocentric view is wrong, which is actually kind of a big deal to figure that out and to get people to accept it. It took a long time and a lot of people died. So the church murders people, in fact. So the celestial sphere, let's start with that. What is that? Okay, just imagine if you're standing on the Earth somewhere, you can see out to the horizon, right? And that's the edge of what you can see. So there's a definition right there, your horizon. But the point right above your head is the zenith. If I was standing over here, my zenith would be over here. It's the point right above your head. So it depends on the person and where they're standing. It's a relative position, the zenith. Okay, the celestial sphere is imagining the coordinate system of Earth, but cast out into the sky. So, for example, I'll go back to yellow here. You've got Earth's equator here. Well, if you imagine that shined out to the sky and imprinted on the stars, then that is the celestial equator. It's the same as Earth's equator, but it's attached to the stars. This person here is in the northern hemisphere, in America somewhere, it looks like, and their zenith on the celestial sphere is some random point up here that changes over time as the Earth rotates and other stuff. The Earth's equator is lined up with the celestial equator, and Earth's North Pole and South Pole are lined up with the North Celestial Pole and the South Celestial Pole. So what am I talking about? We're trying to talk about a coordinate system here. If we just look at Earth, right, if you're here and you want to tell someone here where you are, it's hard to say. How do you communicate to them? Nowadays you'd use GPS or something like that. But in the old days, you just drew a bunch of lines, latitude and longitude. So here's our longitude, here's our latitude. You've got the equator where it's 0. Up here at the North Pole all the way is 90 degrees and down to 0 degrees. And then your latitude in Greenwich in London, from the North Pole through London, through Greenwich Naval Observatory down to the South Pole, that is 0 degrees longitude. And that's how we define the coordinate system. So if somebody says 25 degrees north latitude, 35 degrees east latitude, longitude, or something like that, then with those two coordinates, you could say, oh, I'm here, and then this person could say, oh, I'm here, with their own coordinate system. The whole point of all this is to Do something similar with the stars. Let's say you're looking up on the stars and you see stars everywhere, and you see a massive asteroid and it's coming to crash into Earth. And you call NASA and you say, hey, there's an asteroid coming. And they say, well, where is it? And you say, it's in the sky. And they say, well, where in the sky? The sky's huge. And you say, well, it's over, it's like right by my zenith. And they're like, don't you know your zenith is relative to you? How do I know where your zenith is? Where are you? And so then they have to have this little debate. But if the person calling on the phone, which could be you someday, knows right ascension and declination, which is the coordinate system we use on the sky, they'd be able to say, oh, this star has this coordinate. And that's the whole point of all this, is to define a system so astronomers can communicate to each other where different things are on the sky. Okay, so forward through that. Again, make sure you know the celestial equator. You might have to watch a couple of videos on it online to get a better idea, because it takes a little bit to picture it in your head. Okay, so this is the south celestial pole here. The south celestial pole is, if you go down to the South Pole, there is no south star like there is a north star. If you go down to southern hemisphere and you look and you do a star trail, long exposure image, you see that the stars appear to be rotating around. Well, they're not actually rotating. The Earth is rotating, and when you're at the pole, all the stars at that point appear to orbit around the North Star. And the North Star is at that point, it doesn't appear to move because everything's moving around it and orbiting around it. It's kind of like an ice skater who looks straight up into the rafters when they're spinning so they don't get dizzy, because that will be the lowest amount of motion if they look straight up versus if they tilt their head down. Okay, so anyway, let's see if they talk about this. So no, they define a couple things, so make sure you read through that. So during a 24-hour period, all the stars above the horizon, during a 24-hour period, all stars are above the horizon exactly half the time. Okay, so, and it says, of course, during some of these hours, the sun is too bright to see them. But that's a key point. Here's your horizon. Stars will rise and set just like the sun. Okay, some stars that are close to the North Pole, they never rise or set. They are up all the time. We just can't see them during the day. For example, the North Star is always in the same spot all the time. We just can't see it because of the atmosphere during the day. And that's what this picture is trying to show you. These are called circumpolar stars because they rotate around the pole. Okay, blah. What's your angle? Astronomers measure how far apart objects in the sky by using angles. That's true. Let me delete this. By definition, there are 360 degrees in a circle, so a circle stretching completely around the celestial sphere contains 360 degrees. The half sphere or dome then contains 180 degrees. If two stars are 18 degrees apart, their separation spans about 1/10 of the dome of the sky. To give you a sense of how big a degree is, the moon is about half a degree across. So if you look up on the sky and you see a full moon, that moon is 0.5 degrees across. So then if you imagine going all the way around, that would be 360 degrees. Okay, we don't really use degrees. We use arc seconds and arc minutes, but we'll talk about those in a little bit. Okay, so the sun rises and sets. I don't know if you noticed that, but every day comes up, comes down. Yeah, so this is the important thing. For thousands of years, astronomers have been aware that the sun does more than just rise and set. It changes position gradually on the celestial sphere, moving each day about a degree to the east relative to the stars. So every day, the sun moves a little more than the next day. And this, as you know, the days get longer and the days get shorter, and the sun moves around, which I've noticed it comes into my window now and blinds me at night when I'm trying to sit there. Normally when I sit there, it doesn't. So anyway, I'll get over it. All right, the path the sun appears to take around the celestial sphere each year is called the ecliptic, and it's in figure 2.6. Is that what it says? Figure 2.6. That is not figure 2.6. That's the constellations on the ecliptic. Well, okay. Weird. What this is saying, this is another keyword. This is something you have to know for sure. The ecliptic, okay, is the apparent path of the sun across the sky. So here's your horizon, and here's the sun. It one day it's here, the next day it's here, the next day it's here, next day it's here, next day it's here. Okay, and as it moves across the sky, like that, that path is called the ecliptic. Okay, let me see. Let me delete this. Okay, so blah blah blah. I'm trying to see what this picture is. Star circles at different latitudes. So these three pictures here are showing you if you stand at the North Star, we need to get yellow here. If you stand, there's a little person there standing at the North Star. Their zenith is aligned with the North Pole. So those stars never rise and set. In fact, all the stars, as the Earth rotates, they can see basically from the horizon up. And those stars are going to orbit all the time. They're not going to appear to rise and set. They're going to appear to move around the sky at the horizon, which is a little bit wild. And if you know at the North Pole, half the time of the year, it's, completely dark up there. And when it's completely dark, then you can see this effect pretty crazily. Now, if you are at the equator, standing at the equator, the Earth, so here you are standing at the equator, your zenith is straight up there, and the North Pole is this way, and the Earth rotates that way. So what you see is all the stars rising and setting, all the stars rising and setting, all the stars rising and setting. So if you actually stand at the equator, you can see the entire universe over the course of a year, every star. If you are at the North Pole, you can only see the northern hemisphere. If you're at the South Pole, you can only see the southern hemisphere. You'd never see the northern hemisphere. But at the equator, you can see the full sky. And then at some intermediate latitude, like where we are, then we're tilted. We're at 42 degrees. We see some stars circumpolar, some stars rise and set, and some of the stars down here we'll never see in the southern hemisphere. So definitely you should go out and see them. Okay, so the apparent path of the sun, this picture is the constellation. So let's say in June, right, the sun during the day is going to be on the backdrop behind it, which you can't see, would be the constellation Taurus. You can't see it because the sun's out. And that's what makes up the zodiac, where astrology comes along. And then a couple months or a few weeks later in August, you got the same thing in Cancer over there. And then there you go. Later in August, so I'm a Leo, later in August you get to the Leo constellation, and then Aries and so on. So that's where these constellation comes from. As Earth goes around the sun, okay, as it orbits the sun, the constellations, the stars in the sky, change at night, but also during the day where you can see them. And so that's what makes up the zodiac. All right, continuing on. So here's your definitions of your... my birthday is August 10th. Don't tell anyone. It's private information. And so that makes me Leo. All right. So here you go. The celestial tilt. This is a little bit weird. So the Earth is like a top. Okay? And normally when you spin a top on a table, it rotates around like that. Okay? The Earth is rotating around like that, but since it's in space and it's not sitting on anything, it can rotate around at an angle. So if the sun is here, the Earth goes around the sun like that, and it's got this tilt while it's doing that. And it's going around and around, but at this weird tilt. Okay, so if we have our ecliptic, sorry, not the ecliptic, but our celestial equator for our celestial sphere is at this angle, and our north and south celestial poles are at this angle, then the sun, right, orbits at this angle because we're tilted 23.5 degrees with respect to the sun as we orbit around it. So sun is here, Earth is here, and we're tilted like that. So when we orbit around it, we're at this little bit of a tilt. So 6 months of the year, we're tilted away from the sun. As we get around to this side of the sun, we're tilted towards it. And that's why we have summer. When we're tilted towards it, we get more sunlight. And in winter, when we're tilted away from it, we get less sunlight. And so that's why we have the seasons. All right, so the wandering stars are the planets. The wandering stars are, the stars we can see with our naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. It says Uranus, and most people can't see Uranus. But anyway, those are the wandering stars. So they call them the wanderers. That's what planets means. And it's because the stars appear to slowly move, but the planets move quite a bit. You can watch a planet move across the stars even in a given night a little bit. But even each night, you'll see it move quite a bit more than the stars and the planets. So we got angles in the sky here. Speed is distance over time, so you can calculate the speed that a planet or something moves across the sky by measuring the angular distance it travels, and you know if a planet moves about a full moon's width, that is moving about a half a degree, and you can measure the time, and so you can get the rate and say half a degree per hour or something like that and get its overall speed. So that's what that example is trying to say here. And this check your learning thing is to say, oh, what's the moon doing if I try to estimate that, okay? So you can do that exercise someday, go outside and look at the moon and just see how long it takes to go around. All right, so we've got the zodiac here, which we already described. It's the belt along the ecliptic. Again, make sure you understand what the ecliptic is. You might need to watch a little video or look up some other diagrams because this isn't super clear here. All right, so constellations, right? Constellations are actually states in the sky, like states on the United States. They're boundaries. So, for example, let's look at the constellation Orion. Might be, something more like this, and that's the area of the sky called Orion. But the asterism is this guy with his club here, and he's angry, and he's got a belt, and he's got a sword, and he's got knees and elbows and stuff, and I don't know, that looks about right. And he's got a big shield here, and so that would be the constellation Orion. The asterism is the picture, and the constellation is the area of the sky, defined in a very serious way by folks. So constellation, it says right here, constellation is one of the 88 sectors that we divide into the sky, like the United States is divided into 50 states. It's the exact same idea. The asterism here is the picture, like the Big Dipper is the asterism for Ursa Major. Big Dipper looks like a Big Dipper, but Ursa Major is the constellation, and the actual picture is, if you look at it, is the way people imagine, it's a giant bear, which is kind of weird. Definitely doesn't look like a bear. Okay, so here's a cool link to learning. I definitely recommend doing that. You can construct a sky map. You can also download something called Stellarium, which I recommend you do. It's free. It's on every application and platform, Windows, Mac, and Linux. I believe there's an app on phones, but it's a planetarium software that allows you to just fly around and pick the date and time and see what the sky is doing, and it's pretty cool. So anyway, ancient astronomy. So this is a little bit, you can kind of gloss over this. You don't have to go too in-depth. Astronomy around the world. The Babylonians are super famous for being super smart and developing a lot of mathematics and astronomy. So definitely they had foundations in almost all of the modern science and math. And anyway, they had calendars. Chinese had calendars. All these ancient people had calendars based on the sky, and that way you could plant and farm and predict how things were going to work. We'll talk about comets and meteors later. Chinese astronomers kept records of what we called guest stars suddenly flare up. So we think of these as supernovas, but also there's in 1053, I think it was, that Crab Nebula exploded, basically. Well, the Crab Nebula is what's left behind, but a supernova went off. You could see it during the day, and they talked about that. There's also comets and whatever that, land and pass through the sky and show up, and people think they're weird. Usually they were a sign of bad things for folks, bad omens. And of course, it's totally random. Anyway, I'm so smart now. All right, early Greek and Roman cosmology. Again, we're kind of skipping through this. Blah, blah, blah. So this is an important point, at least 2,000 years before Columbus, educated people in the eastern Mediterranean knew the Earth was round. Okay, the spherical Earth may have stemmed from the time of Pythagoras, who lived 2,500 years ago. He believed circles and spheres to be perfect forms and suggested that Earth should be a sphere, which is a weird argument. So I don't know if we should really say that. But anyway, you can read through this, a little bit of history. One of the first evidences that Earth is round is you look at the shadow on the moon when it casts it during an eclipse. Of course, if you don't know what an eclipse is, then it just looks like the moon's getting a shadow. So that wasn't very convincing back in those days. But one of the most important things here, well, I don't know why they're talking about parallax here for a second. So parallax is, we're going to talk about this a lot. Parallax is a way we can measure the distances to things. And it's just like if you hold your thumb out at arm's length, close one eye, close the other eye, and switch, your thumb will appear to move from your perspective as it shifts from one eye to the other, but your thumb isn't actually moving. And the more it moves, the closer it must be to your face. The further away you move your thumb, the less it'll appear to move. And that's just like when you're driving down the road. You pass by nearby things very fast, but the mountains in the distance don't move very quickly. So that's just a result of parallax. Okay, so it's setting up basically this idea here. How do we know that Earth is round? Well, one of the most important things, and this is something you can easily do, is the Eratosthenes, I can never say his name, Eratosthenes method. Okay, and so this is a little bit tricky, but let's try and explain it. So the Earth is curved. The light from the sun comes in basically parallel no matter where you are on the planet. But this curvature of the Earth, let's say you build a tower right here, okay? You see how this, well, let me actually draw it perpendicular. So if it goes like this, and then goes like, oh, I'm doing a horrible job here. I'm trying to draw this picture again, but this picture is not very clear, and my picture is not very clear either. But basically what happens, since the rays are coming in, if you draw a tower and it's perpendicular to the surface of the Earth here, and then you draw the same tower and it's perpendicular to the surface of the Earth here, you see how the angles are different? This one is 90 degrees to the surface, this one's 90 degrees to the surface. See how they're different angles? So they're going to cast different shadows. And the shadow that they cast depends on the curvature of the Earth. So if you can measure this curvature based on these shadows, you can get the radius of curvature of the Earth. It's the simplest way and the quickest way. You can just set up two webcams, stick two sticks in the ground, and look at their shadows from 100 miles apart, and you'll see that their shadows are different at the same time. And the only way that's possible is if the Earth has a curved surface. The other way is to just not be an idiot, and then you can just realize the Earth is round. Okay, so okay, that's not fair. Could be a conspiracy. I don't know. We've never been to the moon. We've never been. It's the fluoride in the water. Okay, so anyway, there's another concept here that's important to understand, and that's this idea of precession. Okay, so this guy Hipparchus, he's a very famous person, Turkish dude, and he divided stars into magnitudes, which is their brightness basically, and then but he measured this thing called precession. Okay, so basically the Earth, if you spin a quarter and it starts spinning around, and eventually it starts to slow down and it starts to wobble. That's basically what the Earth is doing. It's this giant ball of rock and molten lava spinning around in space with nothing to hold on to, and as it spins around, it kind of wobbles as it rotates. So it's going, it's got a wobble to it. And that wobble means that right now our North Pole is pointed at Polaris, which is the North Star, and that's, if you see that star, you know where north is, and you always can go north. But it takes only 26,000 years for the Earth to precess around as it changes and ends up back to where it is. So 26,000 years it goes through this cycle. So eventually the North Star will be close to north, but not all the way. And eventually Vega will become the new North Star, and Thuban will become the new North Star, and we'll be back to Polaris in 26,000 years from now. So that's kind of a wild thing, and he was the first one to measure that. Okay, that's really interesting. So Ptolemy, pizza's ready. Okay, Ptolemy made a model of the solar system, and let's see where it is. So one of the things that you had a problem with to explain was this, what we call apparent retrograde motion. And it's where a planet, if you watch it on the sky every night, it goes like dink, 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 and appears to go backwards and then continue forward. Well, how can a planet do that? What's it doing dancing on the sky? How do you explain that? And so, especially if Earth is the center of the solar system and Mars is orbiting around Earth, how do you get it to dance? Well, the explanation was that planets orbited around Earth like this. I'm not even joking. That was literally the explanation, and that's how people drew it. But not all planets do that. For example, Mercury and Venus, they orbit in nice circles. Okay, so Mercury and Venus do a nice circular pattern, but all the outer planets, they dance around like they're crazy or something. How do you explain that? Well, it's easy to explain if the sun is the center of the Earth, and if this is Earth and this is Mars, it turns out that Earth will pass Mars as it orbits, and as it passes it, because it's going faster, it will appear to pass it and make it do this little dance. And I'll show a video of this too. And here's a simulation of it, so you should watch that to understand what that is. This is called retrograde motion, so make sure you understand that. Blah, 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 and they're explaining that, but it's stupid. Okay, astrology and astronomy. Astrology, is the idea of your horoscopes and that kind of stuff, and it's about your, so there's your horoscope, astrology here, trying to relate, when you're born, what your personality is, and how much good luck you're going to have in your life, and all these other weird things that don't have anything to do with anything. Anyway, you can read about that. These are your horoscopes here. I'm a Leo. When they ask for your sign, they're talking about your sun sign, the zodiac sign, which is where the sun was when you were born, and so on. But because of the precession and how the Earth is moving around the sky, the constellations of the zodiac slide westward along the ecliptic, going once around the sky every 26,000 years. It's the same idea. So today, the real stars have slipped about 1/12 of the zodiac, which is about the width of one sign. So I was more of a Leo when I was first born than I am today, and it shifts a little bit over time. So that's a little bit weird, and it just shows you how ridiculous that all is. Anyway, you can read about this. I don't really care. Some people really take this stuff seriously. I apologize if you do, and I'm belittling it, but whatever. You can read this, and it's trying to give it fair, kind of really go into it. I probably shouldn't be so rude. All right, 2.4, the birth of modern astronomy here. This is the main thing. So Copernicus came along and he said, no, you don't need these planets doing all these weird dances to get your spirograph retrograde motion coming out. If you imagine Earth is right here, the third stone from the sun, then these planets will all orbit faster than it, so we'll never see that apparent retrograde motion, but we will pass all the outer planets as we orbit, and they will all perform this retrograde motion. This is called the Copernican revolution, and the heliocentric model was replacing the geocentric model. So the heliocentric model is sun-centered, okay, helio. Anyway, that was a big deal. You can read about that. It's important. It has a lot of consequences. It explains the phases of Venus, which Galileo saw. It has phases just like the moon. You can only explain that if Venus is closer to the sun than us. All right, fantastic. And here's Venus phases, another link to learning you can click on to see an example of this. So Galileo, he was locked in his chambers by the Catholic Church, and for probably being a little bit of a jerk about his heliocentric model, but sometimes you got to make a little bit of noise to make change. He did a lot of things. He realized that all objects accelerate at the same rate. If you drop a bowling ball and a golf ball off a building, they'll hit the ground at the same time, even though they have very different masses. So he came up with sort of the first laws of motion. An object in motion will stay in motion. And he was sort of as Newton would say, if I have seen further than others, it is by standing on the shoulders of giants. Galileo was one of the giants that Newton stood on to see further. Galileo was the first person to take a telescope, which people used to look for pirates. He pointed them to the sky. And you can imagine being Galileo and looking at one of these wandering orbs in the sky, and he looked at Jupiter, and he saw Jupiter, and he saw 4 moons orbiting Jupiter, and every night he drew them, and they were moving around. You could imagine what that must have felt like to be the first guy, first human, to look at one of these wandering stars and see that it was actually a tiny planet, not a tiny planet, but a planet with 4 moons. And he must have immediately thought, I am not alone. There's people over there that are looking at me. You could totally imagine that these things could be entire civilizations with, orbiting the same star. I mean, it must have been wonderful to be in that period, to have that kind of experience. Of course, now we know that they are dead, cold, terrible places to be, and you won't want to go anywhere near Jupiter because the radiation would melt you. But anyway, it was a nice thought at the time. Okay, so let's see. Galileo, there's some history there. And that's basically, I guess, it. Yeah, so Galileo really set in stone the Copernican view that the Earth was the center of the universe. His books were on the Church's forbidden list until 1836. Although, right, where the Church had less sway, they were widely read and discussed. It wasn't until 1992 that the Church admitted publicly that it had erred by censoring him, and so on. So this was kind of a big deal. But anyway, there's a lot of good stuff here. The important things, again, make sure you understand the celestial sphere. Make sure you understand precession, the seasons a little bit. How do we know the Earth is round, and those types of things, and constellations. And we'll talk more about this stuff tomorrow. Okay, bye.